This is the Great Pyramid of Giza. For millennia, it stood as the tallest structure on Earth, a massive, solid stone engineering feat rising nearly 150 meters from the desert floor. Measuring its vertical height is impossible with traditional tools. Because the pyramid is a solid mass, you cannot drop a weighted line to its center, and surveying the steep, jagged slopes manually is dangerously impractical. Modern surveyors rely on GPS and laser rangefinders to solve these dimensional puzzles, but ancient civilizations faced this colossal barrier without any mechanical aid. Calculating the structure's height remains a puzzle of perspective rather than physical labor. It is a problem solved by looking away from the stones and toward the logic of the shadows they cast. In the 6th century BCE, a Greek mathematician named Thales traveled to Egypt and proposed a solution that relied entirely on a shift in observation. He realized the answer didn't require massive scaffolding or precision engineering. The data he needed was already projected onto the ground surrounding the monument. His strategy required nothing more than a wooden staff and the natural angle of the sun, proving that an elegant intellectual pivot can bypass a massive physical obstacle. Start with a simple rule of physics. Because the sun is so distant, its rays hit every object in a local area at the exact same angle at any given moment. A vertical stick and its shadow form a right triangle. The pyramid forms a larger geometrically similar triangle because they share the identical sun angle. Therefore, their height-to-shadow ratio is constant. If the stick is half its shadow, the pyramid is half its shadow. This shared geometry acts as a bridge. It allows a mathematician to determine the height of a massive, eye-reachable peak by measuring a small object right next to it. We can see this logic in action by looking at the specific measurements. We plant our stick, measure its shadow, and simultaneously mark the end of the pyramid's massive shadow. A 2-meter stick casts a 4-meter shadow, a 1-to-2 ratio. The object is half its shadow. Simultaneously, the pyramid casts a 140-meter shadow. Because the stick is half its shadow, the pyramid's unknown height is half of 140. The answer is 70 meters. By applying a proportional ratio, a human mind sitting in the dirt could measure the tallest structure on Earth without ever leaving the ground. Is there a way to reach this answer even faster, skipping the fractional math and proportional equations entirely? There is a specific moment during the day when the geometry of the sun simplifies the problem to a 1-to-1 relationship. As the sun arcs to a 45-degree angle, an object's shadow becomes perfectly equal to its physical height. Watch your 2-meter stick. The moment its shadow is exactly 2 meters long, measure the pyramid's shadow. That measurement is the exact vertical height of the pyramid. This method demonstrates the power of observing natural patterns. By aligning the measurement with the sun's cycle, the need for arithmetic vanishes. When we look at the Giza Plateau today, we see more than just a burial ground. We see a landscape fully quantified by ancient minds. These monuments were understood and measured by a civilization that completely lacked the mechanical precision we take for granted. A grasp of proportion and geometry functioned as a primary instrument, allowing them to map a massive physical environment using only light and shadow. It is proof that human intelligence and basic mathematical principles can conquer the world's most imposing structures, regardless of the scale.